Hi friends, today we start the new question related to symmetry operation. The question is classify the following molecule. Classify the following molecule into appropriate point group. Into appropriate point group. Appropriate point group. Or again the question is other, give the basic requirement of point group with related to example water and ammonia. Or the question is again the another way, give basic requirement of point group related to example water. Okay, this is the question. Classify the following molecule into appropriate point group or give the basic requirement of point group related to ammonia, related to water molecule. Okay, basic requirement means what? Here basic requirement exists. First is the existence of identity. Okay, existence of identity means what? Here AE is equal to EA is equal to AE or AE is equal to EA. Okay, this is called the existence of identity. Okay, then next is the existence of inverse. Existence of inverse. A inverse is equal to A inverse, which is equal to A inverse A. This is called as the existence of inverse. Then next is the abelian. Okay, abelian, that means AB is equal to BA. Okay, now we consider the example. You have to complete that basic requirement on water molecule. Okay, now we take the water molecule here, H1 and H2. This is the structure of water molecule. Now we start this properties. We have to perform this operation, abelian rule, on water molecule. AB is equal to BA. That means you have to take the symmetry operation. You have to replace that A and B by symmetry operation. And now we perform this symmetry operation. See here, water molecule, then you have to perform here C2. Okay, when you perform the C2, at that time what happened? That access is passing to this oxygen, so H2 goes to here, H1 goes to here. See here, H2 and H1. Okay, the next operation is sigma H. Okay, sigma H. When you perform the sigma H means you have to pass the plane. So at that time the position of H2 and H1 has not changed. So H2 as it is, H1 as it is. Okay, now you have to complete that symmetry operation. First this one, now second one. Okay, when you consider this AB, at that time C2 is the first operation, sigma is the second operation. But in the next step you have to perform second operation by first and A operation at the last. Okay, now first operation is sigma H. See here, okay, H1, H2. When you perform sigma H, at that time what happen here? Same way. Okay, H1, H2. Okay, then next you have to perform the C2. At that time what happen? You have to pass the axis from the center. At that time the bond get shifted. At that time what happen? H2 goes here, H1 goes here. See here, the structure is again same, H2, H1, H2, H1. That means both the structures are same. Then here the abelian group is proved. Okay, the next is the fourth rule of existence is associativity. Associativity. Okay, this is the fourth rule of existence. What is the rule here? A in bracket BC, which is equal to AB in bracket C. Okay, when you perform, again you have to consider the water molecule. Here water molecule is here H1, H2. Okay, when you perform the C2, at that time what happen? H2 goes here, H1 goes here. So you have to write here H2 and here H1. The next operation is the sigma V1. Okay. Okay, in water molecule, two vertical planes are present. The plane passing to the center of axis here and the plane passing to H2 and H1. When you perform the sigma V1, that means when you pass the plane from this, at that time H1 is replaced by H2. See here, H1 goes here, H2 goes here. The next symmetry operation is sigma V2. Okay, when you perform the sigma V2, at that time what happened? The plane passing to this, at that time what happened? The H1 is remain as it is. See here H1 and H2. Then in the next step what happened? A, B in bracket C. Again you have to take the water molecule H1, H2, and what is here? You have to consider this operation is first sigma V2. At that time what happened? The H1 and H2 remain as it is, H1 and H2. Then next symmetry operation is sigma V1. Okay, you have to change the priority of that symmetry operation. First, in the previous step what happened? C2, then sigma V1, then sigma V2. In the next step you have to perform the sigma V2, then sigma V1. At the last you have to perform the C2. When you perform the sigma V1, that means you have to pass the plane from this, then H2 is replaced by H1, H1 is replaced by H2, here H2, here H1. And in the next step, when you perform the C2 operation, C2 means you have to rotate this molecule. At that time what happened? H1 is replaced by H2 and H2 is replaced by H1. See here, H2 is goes to the H1, H1 is goes to the H2. Okay, this is the symmetry operation of water molecule. Okay, and that whole molecule is similar to this. So here again the associativity rule is proved. That means when you perform C2, sigma V1, sigma V2, you get this molecule. When you perform sigma V2, sigma V1 and C2, you get this molecule. Okay, and both the structures are same. Here this is the basic requirement of molecule. First rule is the existence of identity, then existence of inverse, then abelian rule, then associativity rule. Here same way you have to take the ammonia molecule and you have to perform the symmetry operations with the help of this rule. Okay, then next question is for trigonal planar molecule. This is the next type of question. For trigonal planar molecule, planar AB3 molecule, find the reducible representation. Find the reducible representation for which sigma bond forms the basis, and find out which orbital from A atom will offer for sigma bonding. Okay, sigma bonding. Okay, what is the question? For trigonal planar AB3 molecule, find the reducible representation for which sigma bond forms the basis and find out which orbital from A atom will offer for sigma bonding. That means in the place of AB3, any molecule is there, but that molecule is trigonal and planar. The example of this type of AB3 trigonal planar molecule is BF3. What is the structure of BF3? Here boron is the center atom, here fluorine, here fluorine, and here fluorine. This is the structure of BF3 molecule. Okay, boron is the center atom, here 3 fluorines are present. This molecule is planar. See here, this is the structure of BF3 molecule. When you consider the BF3 molecule, BF3 means what here? Center is the boron atom is there and remaining 3 fluorines are present. See here, this is the central boron atom, first fluorine, second fluorine and third fluorine. The symmetry operation of BF3 molecule is we already see in the previous lecture. Okay, this is the 2 fluorine, this is third fluorine. Okay, when you this molecule is planar. Okay, all the bonds are present on the plane, trigonal planar molecule. When you pass the axis, at that time all bonds get rotated. So every molecule possesses its identity. So identity operation is present. You have to write in deep. I just write here every molecule possesses its identity. So identity operation is present. Okay. Boron, you have to write the whole information about the molecule. Boron is the central atom. 3 fluorines are present. Okay. This molecule is planar. This molecule is trigonal. You have to write all information about the molecule. Then you have to start the symmetry operation of BF3. The first line of molecule is every molecule possesses its identity. So identity operation is present. Then axis, here inversion is absent. On opposite side, on equidistance, on the opposite direction, there is no same atom. I is absent. Then next is the axis. When you pass the axis center, at that time the 3 bonds get rotated. So here C3 is principal axis. So C3 generate C31, C32, C33, which is equal to identity. So twice C3 are present. Then the plane sigma H is present. Then the plane passing to the center of axis and one of the subsidiary axis. So here 3 sigma V are present. Then next is improper axis of rotation. Rotation followed by reflection and reflection followed by rotation, you get same structure. So here twice S3 are present. Okay, so see here the total symmetry operations are here, identity is present. Okay, then next inversion is absent, twice C3 is present, then remaining subsidiary axis. Okay, when you consider the subsidiary axis, when you pocket this boron and fluorine bond, okay, this is C21, C22, again this is C21, C22, C21, C22. That means each C2 is passing to this this boron fluorine. Okay, C2 generates C21, C22, which is equal to identity C21, C22, which is equal to identity C2 generates C21, C22, which is equal to identity. That means how many C2 are present? Thrice C2 are present. Then next one is the twice S3 are present, sigma H to sigma V. So the total symmetry operations are, see here, identity, then next one is the twice C3, then thrice C2, then twice S3, see here, twice S3, then next sigma H and then thrice sigma V. So total symmetry operations 1, 2, 3, 6, 7, 8, 9, 10, 11, 12. H is order of the group is 12. Okay. This is up to, this is the symmetry operation, total symmetry operations are 12. Then the point group is, you have to consider the principal axis, C is perpendicular to sigma H. So C get converted to D. Here C3 is there, so you have to write here 3. Here sigma H is there, so D3H. That C3H, that means when the principal axis is perpendicular to the sigma H, C get converted to D. This is the point group of D3H. Okay. Then next is the classes. How many classes are present? 1, 2, 3, 4, 5, 6. 6 classes are present. Okay, then next. Okay, this is the character table D3H. Okay, your molecule is BF3. Okay, this is the structure of BF3. D3H is the point group. In question, the question is you have to find out the total reducible representation for which sigma bond forms the basis, and you have to find out the orbitals from the A atom will be offered for the sigma bonding. Okay, this character table is given in the question paper on the last page. Okay, now this is the point group of BF3 molecule. The point group is D3H. At that time, when the question is like that, at that time you go through the D3H point group. This D3H point group, when the question is on the same way, at that time the point group of D3H molecule is present on, is given on the question paper on the last page. Okay, D3H. Here total classes are there. The total classes of BF3 molecule is 6. 1, 2, 3, 4, 5. Okay, 6 classes are there. Okay, this is called the tau 1, tau 2, tau 3, tau 4, tau 5 and tau 6. The symbol is like that, tau. Okay, this is the tau 1, tau 2, tau 3, tau 4, tau 5 and tau 6. This is called as a Mulliken symbol. What is the name here? Mulliken symbol. Mulliken symbol. This Mulliken symbol is already given in the question paper. Tau 1, the Mulliken symbol for tau 1 is the A1 dash, next A2 dash, E dash, A1 double dash, A2 double dash, E double dash. This is called as a Mulliken symbol. This Mulliken symbol is given in the question paper in this character table. Okay, then you have to find out the total reducible representation, TR. Okay, in character table you have to find out only the TR. TR means what? Total reducible representation. That means when you perform the identity operation, on BF3 molecule, at that time all the bonds are present on the same place, so the TR, total reducible representation for identity molecule, is 3. That means what? When you perform the rotation, जेवढे बॉन्ड्स त्यांची जागा बदलत नाहीत त्याला म्हणतात TR. जर तुम्ही आयडेंटिटी ऑपरेशन या मोलेक्युलवर केलं तर मोलेक्युल ॲज इट इज राहतो. म्हणजेच काय होते, 3 बॉन्ड्स आहेत ते ॲज इट इज राहतात. सो द TR फॉर आयडेंटिटी, सो हियर thrice. Okay, when you perform the principal axis here, all the bonds get rotated its position. That means it change its position. So TR for C3 is 0. Then next, when you perform the C2, okay, see here, this is the thrice C2s are present on each axis. This is C21, C22. That means one bond is not change its position. Okay, when you pakad that bond, C21, C22. Okay, so TR, total reducible representation for C2 is 1. Again, when you consider sigma H, the sigma H means plane. Here when you perform the sigma H, at that time 3 bonds are present on the same position, so total reducible representation for sigma H is 3. Okay, when you perform the S3 operation, at that time, S means what? Improper axis of rotation. Again, when you perform rotation, at that time what happen? All the bonds get rotated, so TR for S3 is 0. Okay, then next is the vertical plane, the plane passing to the principal axis and one of the subsidiary axis. That means what happen when you pass the axis here, this bond is not change its position, so the TR, total reducible representation for sigma V, is 1. That means you have to write the unchanged vector. TR means what? Unchanged vector. जे वेक्टर त्यांची जागा बदलत नाहीत त्या वेक्टर्सला म्हणतात TR, total reducible representation. Okay, then we start the answer. Okay, what is the rule? Summation of Li square. Okay, what is the rule here? Summation of Li square, which is equal to order. Order means what? H. Here order of the group is 12. Okay, what is the order? You have to write the total symmetry operations. H is equal to 12. Okay, Li means what? Here you have to put the values in Li. Okay, when you consider here 1 square, 2 square, see here 1, you have to consider L1, L2, L3, L4, L5, L6. Okay, L1 square plus L2 square plus L3 square, okay, plus L4 square plus L5 square plus L6 square, which is equal to order, that means 12. You have to put the values. See here 1 square plus 1 square plus 2 square plus 1 square plus 1 square plus 2 square, which is equal to 2. You just put the values of L. Now by using the reduction formula, what is the reduction formula? See here Aj is equal to 1 upon H. H means what? H is the order of the group. What is the rule here? 1 upon H, summation of Gp, then GIR, GJR. Okay, this is the rule. 1 of Aj is equal to 1 upon H, summation of Gp, Gi. What is here? GIR, GJR. G means what? You have to write this symbol, that is called as a Gi. Okay, then GIR, GJR. Okay, this is the rule. By using this rule, you have to find out, you have to perform the next step. Okay, for TR1. Okay, TR tau 1. See here TR tau 1. What is here? You have to put the values. 1 upon H means what? H is the order of the group, that means 12. GIR, GJR. Then see here identity. You see the number of identity here. There is no number here, 2 is there. Here number is not present, so you have to consider here 1. Here 2 is there. You have to find out the for tau 1. That means 1 into 3 into 1. Okay. When you perform the TR tau 2, 2 into 0 into 1. When you perform the for T2, E into 3 into 1. Okay. And the same way, see here, you have to put the values 1, see here, in bracket 1 upon H means what? 1 upon 12. Okay. See here 1 into 3 into 1. 1 into 3 into 1 plus 1 into 3 into 1. Okay. Again 1 into 3 into 2. See here. The next is 2 into 0 into 1. You have to find out the product of this A. Just 2 minutes. Okay. You have to find out the product for tau 1. 1 into 3 into 1. Then 2 into 0 into 1. See here. 2 into 0 into 1 plus 3 into 1 into 1 plus 3 into 1 into 1 plus there is no number here, so you have to consider here 1. 1 into 3 into 1. 1 into 3 into 1. Okay. 1 into 3 into 1. Again here number is 2. 2 into 0 into 1. 2 into 0 into 1. Then next is 3 into 1 into 1 plus 3 into 1 into 1. So the value is 1 upon 12. See here 1 into 3 into 1 means what? 3 plus here 1. Okay. Here 2 into 0. Here 0. Then 0 into 1. So next is the 3 plus 3 plus 3 plus 3. How many is here? 3 plus 3 plus 3 plus 3. That means the 12. 1 upon 12 in bracket 12. So we get the value is here 1. Okay. In the same way, you have to find out the representation for TR into tau 2. Okay, now we find out the Tr tau 1. Now we find out the Tr tau 2. Okay, same way. You have to put the value 1 upon 12. Then see here, 1 into 3 into 1, 2 into 0 into 1, 3 into 1 into minus 1, 1 into 3 into 1, 2 into 0 into 1, 3 into 1 into minus 1, and we get the here values is, your answer is 0. Okay, then for Tr into tau 3, again you have to find out for tau 3. Tau 3 means what this is. Okay, again here there is no number, you have to consider here 1 into 3 into 2, 2 into 0 into minus 1, 3 into 1 into 0, 1 into 3 into 2, 2 into 0 into minus 1, 3 into 1 into 0, again you get this value is 1. Okay, then Tr tau 4, again in the same way you just put the values, then you get the answer. You have to put here value Tr for tau 4, again 1 into 3 into 1, 2 into 0 into 1, 3 into 1 into 1, 1 into 3 into minus 1, 2 into 0 into minus 1 plus 3 into 1 into minus 1. Then we get the answer here 0. Then you have to find out for Tr into tau 5. In the same way, you again get the answer is 0. Then Tr for tau 6, the answer is 0. That means here you have to find out the total representation. Here tau 3 is answer 1. Okay, and the Tr tau 1, the first for Tr tau 1 is also 1. This is Tr tau 2, Tr tau 3, Tr tau 4, Tr tau 5, Tr tau 6. You have to find out the representation having the non-zero vector. Okay, Tr tau 2 is 0, Tr tau 4 is 0, Tr tau 5 is 0, Tr tau 6 is 0. That means the only the Tr tau 1 and Tr tau 3 having the value is 1. Okay, so you have to consider the tau 1 and tau 3 forms, what is here, tau 1 and tau 3 form the set of representation. In question, what is the question here? You have to find out the set of irreducible representation. So from that we get the answer tau 1 and tau 3 forms the set of irreducible representation. Irreducible representation, because this product is not 0, this product is 1. Those products are 1, that forms the set of irreducible representation. Then again the tau 1 goes to the s and tau 3 goes to the p orbital. So the hybridization of this molecule is sp2. Okay, that in question paper the Tr tau 1, Tr tau 3, the set is already given. You have to find out those vectors are non-zero vectors. This forms the set of orbital. You just see the orbitals in front of non-zero, then we get the answer. This is all about the question. The basis of find out the orbitals forms the sigma bonding. Okay, thank you.